Close your eyes for a moment. Feel the darkness settle around you like a soft blanket. Now open them again. The world returns in an instant. Colors bloom. Shapes emerge. Your room becomes real once more. This simple act of opening your eyes reveals one of the universe's most beautiful mysteries. Light. Light is always dancing around you. Even now, as you read these words, billions of tiny particles of light are bouncing off this page. They leap toward your eyes like invisible messengers, carrying the story of black ink and white paper. But light is more than just the brightness that fills your day. It moves in ways that seem almost magical. When light hits water, it bends. When it meets a mirror, it bounces back perfectly. When it passes through a prism, it splits into rainbows. Think of light as an ancient dancer who has been performing the same graceful routine for billions of years. This dancer moves faster than anything else in the universe. In the time it takes you to blink, light could travel around the entire Earth 7 times. Yet for all its incredible speed, light follows very simple rules. These rules are like the steps of a dance that never changes. Understanding these steps is the first secret to understanding how invisibility might be possible. Imagine you are sitting by a calm lake at sunset. The golden light from the sun travels 93 million miles through empty space. It enters our atmosphere and begins to slow down just slightly. As it reaches the surface of the lake, something beautiful happens. Some of the light bounces off the water like a rubber ball bouncing off a wall. This reflected light carries the image of the sunset to your eyes. That is how you see the golden ripples dancing on the surface. But some of the light does something different. It enters the water and bends. This bending happens because light moves more slowly through water than through air. It is like a runner who must slow down when moving from a smooth track onto soft sand. When light bends as it enters water, we call this refraction. This single word holds enormous power. Refraction is one of the key ingredients in making things invisible. You have seen refraction many times, even if you did not know its name. When you put a straw in a glass of water, it appears to break at the surface. The underwater part of the straw seems to be in a slightly different place than it should be. This is refraction playing tricks with your eyes. The light bouncing off the underwater part of the straw bends when it exits the water. Your brain, which expects light to travel in straight lines, is fooled. It sees the straw as broken, even though it is perfectly whole. This gentle trickery of light is everywhere around you. The bottom of a swimming pool appears closer than it really is because of refraction. A coin at the bottom of a fountain seems to shimmer and dance. The air above a hot road on a summer day creates shimmering mirages. Each of these effects happens because light is bending, changing direction, following the rules of its ancient dance. Now here is where the story becomes even more interesting. Different materials bend light in different ways. Glass bends light more than air. Water bends it more than glass. Diamond bends light even more than water. Scientists have discovered that every material has its own special relationship with light. They measure this relationship with a number called the refractive index. Air has a refractive index close to 1. Water is about 1.3. Glass is usually around 1.5. Diamond is over 2.4. These numbers might seem small and unimportant, but they represent something profound. They tell us exactly how much light will bend when it moves from one material to another. Think of it this way. Light is like a river flowing downhill. When the river meets rocks and boulders, it must change course. The bigger the boulder, the more the river must bend around it. Materials with higher refractive indices are like bigger boulders in the river of light. Scientists realize something remarkable about these numbers. If they could control exactly how light bends, they might be able to guide it around objects. Instead of light bouncing off something and revealing its presence, the light could flow around it like water flowing around a smooth stone. This is the first glimpse of how true invisibility might work. Not by making things disappear like magic, but by convincing light to dance around them. The idea sounds simple, But making it work in the real world requires materials that do not exist in nature. It requires understanding light more deeply than anyone had ever understood it before. Light carries information. When light bounces off your face, it carries information about the color of your eyes, the shape of your nose, the texture of your skin. This information travels to someone else's eyes, and they see you. But what if light could flow around you without ever touching you? What if the light that should have bounced off your face could somehow be guided around your entire body and then continue on its way, completely unchanged? To anyone watching, it would be as if you were not there at all. The light would carry no information about you. It would be as if you had stepped out of the river of light entirely. This is the dream of the invisibility cloak. Not a magical garment that makes you vanish, but a sophisticated manipulation of light itself. A way to choreograph the ancient dance of light so perfectly that you become hidden within its steps. The science behind this dream is real. The physics is solid, but the engineering challenges are enormous. As you settle deeper into your pillow tonight, let your mind wander through this dance of light. Feel the photons streaming past you in the darkness. Imagine them bending and flowing like invisible rivers all around you. Tomorrow, we will explore how your own eyes participate in this dance and why understanding vision is the next step toward understanding invisibility. Right now, as you read these words, your eyes are performing miracles. They work so quietly, so smoothly, that you never think about what they are actually doing. But understanding your eyes is like discovering a secret doorway into the mystery of invisibility. Your eyes are not cameras, though people often say they are. Cameras capture everything in front of them equally. Your eyes are far more clever than that. They are selective witnesses, choosing what deserves your attention. Think of your eyes as two gentle fishermen sitting by the river of light. All day long, photons flow past them like silver fish in a stream. Your eyes cast their nets carefully, catching only the photons that carry the most important messages. Each eye contains about 120 million rod cells and 6 million cone cells. These tiny sensors line the back of your eye like audiences in a vast theater. When photons strike them, they whisper their secrets. The rods speak of brightness and darkness. The cones tell stories of color. But here is the truly remarkable part. Your brain does not simply accept these whispered messages. It interprets them. It fills in gaps. It makes assumptions. And sometimes it can be beautifully fooled. You have a blind spot in each eye where your optic nerve connects. It is about the size of 6 full moons placed side by side. Yet you never notice this blind spot because your brain simply paints over it with what it thinks should be there. This gentle deception happens constantly. Your brain is always guessing, always filling in details, always trying to make sense of the incomplete picture that light provides. This is why magic tricks work. This is why camouflage succeeds. This is why invisibility might be possible. When you look at something red, you're not seeing redness itself. You're seeing light waves that are about 700 nanometers long. These waves bounce off the object and travel to your eyes. Your cone cells detect these specific waves and send signals to your brain. Your brain translates these signals into the experience you call red. But what if those light waves never reach your eyes? What if they were somehow guided around the object instead of bouncing off it? Your cone cells would have nothing to detect. Your brain would receive no signals about that spot. To you, there would be nothing there at all. This is the first principle of invisibility. It is not about making things disappear. It is about preventing light from carrying information from the object to your eyes. Your eyes evolved to notice certain things very well. Movement catches your attention immediately. This helped your ancestors survive by spotting predators or prey. Bright colors stand out because they often signal danger or food. Sharp edges and contrasts draw your focus because they usually mark the boundaries between different objects. But your eyes are not good at noticing things that remain perfectly still. They struggle with objects that match their surroundings exactly. They can be confused by patterns that break up familiar shapes. This is why a leopard's spots help it vanish in dappled sunlight. Why a stick insect looks exactly like a twig. Why military camouflage uses broken patterns instead of solid colors. These natural and artificial disguises work because they understand how your eyes see the world. Your eyes also have limitations that scientists are learning to exploit. You can only see a tiny slice of all the light that exists. The visible spectrum, as scientists call it, runs from violet light at about 380 nanometers to red light at about 700 nanometers. But light comes in many other flavors that your eyes cannot taste. Infrared light carries heat. Ultraviolet light causes sunburns. Radio waves carry music and voices. X-rays can see through your body. All of these are forms of light, just light that your eyes cannot catch. This means that something could be perfectly visible in infrared light while being completely invisible to your eyes. Military aircraft use this principle. They're designed to avoid reflecting radar waves, even though they might be clearly visible to someone looking at them directly. The reverse is also true. Something could be invisible to your eyes while being perfectly visible to other forms of detection. This is why true invisibility is so challenging. It is not enough to hide from human eyes. A perfect invisibility cloak would need to hide from all forms of light. Your eyes work together as a team, creating something called binocular vision. Each eye sees the world from a slightly different angle. Your brain compares these two views and uses the differences to judge distance and depth. This teamwork creates another challenge for invisibility cloaks. The cloak would need to bend light perfectly for both of your eyes simultaneously. It would need to account for the fact that you might move your head, changing the angles from which you view the hidden object. As you blink, your eyes perform their own small magic trick. For about 300 milliseconds every day, you're technically blind while your eyelids close. Yet you never notice these tiny moments of darkness because your brain smoothly fills in the gaps. This reveals something profound about how you see the world. Vision is not just about light entering your eyes. It is about your brain constructing a story from the pieces of information that light provides. Change the information, and you change the story. When you look at a rainbow, you're seeing white sunlight separated into its component colors by water droplets in the air. Each color bends slightly differently as it passes through the water. This separation reveals that what appears to be simple white light is actually a symphony of different wavelengths traveling together. Your eyes have learned to read this symphony. They can distinguish millions of different colors, each one a unique combination of wavelengths. They can detect incredibly faint light, single photons arriving after traveling for billions of years from distant stars. Yet for all their sensitivity and sophistication, your eyes remain wonderfully, usefully imperfect. They make assumptions. They fill in blanks. They focus on what seems important and ignore what seems ordinary. Understanding these gentle imperfections is key to understanding how invisibility might work. The goal is not to eliminate light entirely, but to guide it in ways that your eyes and brain cannot detect or interpret. As you prepare for sleep tonight, notice how your eyes gradually adjust to the growing darkness. Feel them relaxing, releasing their careful watch over the world around you. In dreams, your eyes will close, but your mind will continue to see impossible things. And tomorrow, we will explore how certain materials can bend light in ways that seem almost as impossible as dreams. Imagine holding a piece of clear glass in your hands. It feels solid, heavy, real. Yet when you look through it, light passes through as if the glass were not there at all. This simple miracle happens because of the way atoms dance together inside the glass. Every material in your world has its own relationship with light. Wood blocks it completely. Water lets it through but bends it gently. A diamond captures it and sends it sparkling in all directions. Each substance treats light differently because of how its atoms are arranged. Think of atoms as tiny dancers in an enormous ballroom. In some materials, like metals, the dancers move freely, flowing from one partner to another. When light tries to enter this dance, the free-moving dancers absorb it completely, turning light into heat. This is why metals are opaque. In other materials, like glass, the atomic dancers are locked in more rigid formations. They cannot move freely, but they can still vibrate in place. When light enters their dance, they accept it gracefully, holding it for just a moment before passing it along to the next group of dancers. This molecular choreography determines everything about how you see the world around you. The reason you can see through a window, but not through a wall, comes down to how atoms are arranged at scales too small for your eyes to detect. Scientists have learned to read this atomic dance. They can predict exactly how any material will interact with light just by understanding how its atoms fit together. More importantly, they have begun to design entirely new materials with atomic arrangements that do not exist in nature. Glass has a refractive index of about 1.5. This means light travels about 1.5 times slower through glass than through empty space. The light bends when it enters the glass and bends again when it exits, but it emerges largely unchanged. Water bends light even less, with a refractive index of 1.33. This is why objects underwater appear closer than they really are. The light from the object bends as it exits the water, creating a gentle illusion that your brain interprets as distance. But what if scientists could create a material with a refractive index of exactly 1.0? Such a material would be completely invisible. Light would pass through it without bending at all, as if the material were not there. The light would carry no information about the material's presence back to your eyes. This perfect invisibility remains a dream, but scientists have created materials that come surprisingly close. They use techniques that seem almost like magic, arranging atoms in patterns so precise that they can control light with extraordinary accuracy. Some crystals can split light into two separate beams, each traveling at a slightly different speed through the material. This splitting creates beautiful effects, like the double images you sometimes see when looking through certain types of clear stone. It also opens possibilities for manipulating light in ways that nature never intended. Liquid crystals, the same materials used in computer screens and digital watches, can change their relationship with light when electricity passes through them. One moment they might block light completely. The next moment they might let it pass through freely. This electronic control over light opens doors to invisibility devices that could be switched on and off at will. Fiber optic cables demonstrate another way materials can guide light along predetermined paths. Inside these thin glass threads, light bounces back and forth between the walls, traveling for miles without escaping. The cable guides light around corners, through loops, in any direction the cable leads. This guided light reveals a profound possibility. If scientists could create materials that guide light around objects the same way fiber optic cables guide light through themselves, they could create true invisibility cloaks. The challenge lies in creating materials with the right atomic structure. The atoms must be arranged in patterns that convince light to flow around an object rather than bouncing off it. These patterns must be smaller than the wavelength of light itself, requiring precision at scales that approach the atomic level. Scientists call these engineered materials metamaterials, meaning materials beyond what nature provides. Each metamaterial is designed atom by atom to have specific properties. Some can bend light backwards in directions that violate our everyday understanding of physics. Others can focus light more precisely than any natural lens. The most promising metamaterials for invisibility contain tiny metal structures arranged in repeating patterns. These structures are so small that thousands of them could fit across the width of a human hair. Yet their precise arrangement gives the material its light-bending powers. When light encounters one of these metamaterials, it does not simply pass through or bounce off. Instead, it enters a carefully choreographed interaction with the metal structures. The light slows down, speeds up, changes direction, and emerges with its path completely altered. Creating these materials requires tools that can work at nearly atomic scales. Scientists use electron beams to carve patterns into thin sheets of metal. They grow crystals one atomic layer at a time. They use light itself to write structures into specially prepared materials. Each metamaterial is designed for a specific purpose. Some work only with particular colors of light. Others function only when light approaches from certain angles. The most advanced metamaterials can manipulate multiple colors simultaneously, but even these have limitations. The dream is to create a metamaterial that works perfectly for all colors of light, from all angles, in all conditions. Such a material would be the ultimate invisibility cloak, capable of hiding objects completely from human eyes. But even imperfect metamaterials reveal the power hidden in atomic arrangements. They show that the familiar rules of light and matter can be rewritten by those who understand the deepest levels of how reality works. Temperature affects how atoms dance, and this changes how materials interact with light. Heat makes atomic dancers move more wildly, while cold makes them settle into more predictable patterns. This is why some metamaterials must be kept at very low temperatures to function properly. Time also plays a role in this atomic choreography. Some materials change their properties gradually as they age. Others can switch between different states almost instantly when triggered by light, heat, or electricity. Understanding these temporal effects is crucial for creating practical invisibility devices. The most exotic metamaterials challenge our basic understanding of what materials can be. Some have negative refractive indices, bending light in directions that seem impossible. Others can make light appear to slow down or speed up beyond its normal limits. A few can even make light seem to travel backwards in time, though this effect only works over very short distances. As you lie in the darkness tonight, surrounded by materials both familiar and mysterious, consider the hidden complexity in every substance around you. The wooden bed frame, the cotton sheets, the metal springs, all contain their own atomic choreographies, their own relationships with light. And in laboratories around the world, scientists continue to compose new atomic dances, seeking the perfect arrangement that will finally make the impossible dream of invisibility become beautifully, wondrously real. On a hot summer day, you have probably seen water shimmering on the road ahead of you. As you walk closer, the water disappears. It was never really there at all. You have witnessed one of nature's most beautiful magic tricks, a lesson in how temperature can make light lie to your eyes. This phantom water is called a mirage. It happens because hot air and cool air bend light differently. The road absorbs the sun's energy and becomes very warm. The air just above the road heats up too, becoming less dense than the cooler air above it. Light travels slightly faster through hot, thin air than through cool, thick air. When light from the sky tries to reach your eyes, it must pass through these layers of different temperatures. As it moves from cool air into hot air, it bends away from its straight path. The result is magical. Light from the blue sky above gets bent so much that it appears to be coming from the road itself. Your brain, which expects light to travel in straight lines, interprets this as a reflection. It sees blue sky reflected in water that is not there. This is nature's own invisibility cloak in action. The hot air does not make anything disappear, but it creates convincing illusions. It shows you things that are not where they appear to be. It hides the true path of light behind layers of bending air. Desert travelers have known about mirages for thousands of years. They have seen lakes that vanish as they approach. They have watched distant mountains dance and shimmer like underwater castles. They have learned not to trust their eyes when heat makes the air itself become a lens. But mirages are not limited to deserts and hot roads. On very hot days, you might see them rising from parking lots, sidewalks, or any surface that absorbs a lot of sunlight. Even a hot car hood can create tiny mirages that make the air above it seem to ripple like water. The science behind mirages reveals something important about invisibility. Temperature differences in air can bend light just as surely as glass or water can. This means that controlling temperature might be another way to control how light behaves. Scientists have discovered that they can create artificial mirages using carefully controlled heating. By warming air in specific patterns, they can make objects appear to be in different locations than they really are. They can even make objects seem to disappear entirely by bending light around them. This technique works because hot air acts like a lens that is constantly changing shape. As the heated air moves and swirls, it creates a shifting, fluid lens that can bend light in complex ways. Unlike solid lenses made of glass, these air lenses can change their properties from moment to moment. Imagine looking through a piece of glass that is constantly melting and reshaping itself. Sometimes it might magnify things. Sometimes it might make them appear smaller. Sometimes it might bend their images so much that they seem to vanish entirely. This is what happens when light passes through heated air. The ocean creates its own version of mirages. Sometimes ships appear to float in the sky above the horizon. This happens when layers of warm and cool air over the water bend light from distant ships, making them appear higher than they really are. Sailors call this phenomenon a superior mirage. On very calm days, you might see an entire city reflected upside down in the sky above the real city. These superior mirages can be so detailed that you can make out individual buildings and streets. They occur when temperature differences in the atmosphere create natural lenses that project images across great distances. Even your own body creates tiny mirages. On a cold day, your warm breath creates small temperature differences in the air. These differences can bend light slightly, creating subtle distortions in your vision. The effect is usually too small to notice, but it is always there. Birds use these temperature effects to their advantage. Large birds like eagles and hawks seek out columns of rising warm air called thermals. These thermals not only help the birds soar without flapping their wings, but they also create visual distortions that can help hide the birds from their prey below. The northern lights, or aurora, create their own kind of optical illusion. These dancing curtains of light in the sky can make distant objects appear closer or farther away than they really are. The charged particles that create the aurora also affect how light travels through the upper atmosphere. Lightning creates instant, powerful temperature changes that can bend light in dramatic ways. During thunderstorms, some people report seeing objects that appear and disappear in the flickering light. These are likely mirages created by the rapid heating and cooling of air around lightning bolts. Even moonlight can create mirages. On very clear nights, temperature differences between the ground and the air can bend moonlight enough to create ghostly illusions. Ancient peoples sometimes interpreted these lunar mirages as spirits or supernatural beings. Scientists study mirages not just because they are beautiful, but because they reveal the fundamental relationship between temperature, air density, and light. By understanding how natural temperature differences bend light, researchers can learn to create artificial temperature patterns that bend light in predetermined ways. This research has led to the development of heat-based camouflage systems. These systems use controlled heating to create air lenses that can hide objects from view. Unlike materials-based invisibility cloaks, these systems can be turned on and off simply by controlling the temperature. The challenge with temperature-based invisibility is that it requires a lot of energy to heat air effectively. It also works best in still conditions, since wind can disrupt the carefully controlled temperature patterns. But for certain applications, this approach offers unique advantages. Water can create mirages too. When sunlight heats the surface of a lake or ocean unevenly, it creates temperature layers that bend light. This is why objects underwater sometimes appear to shimmer and dance. The water acts like a constantly moving lens, bending and redirecting the light that passes through it. Even ice can participate in nature's light-bending tricks. On very cold days, ice crystals in the air can create optical effects called sundogs or light pillars. These phenomena happen when light bounces off or passes through ice crystals that are arranged in specific patterns by air currents. As you settle into sleep tonight, imagine the invisible rivers of different temperatures flowing around you. Feel the gentle currents of warm and cool air that surround your resting body. Consider how even the simple act of breathing creates tiny temperature differences that bend light in ways too subtle for your eyes to detect. And in your dreams, perhaps you will see the shimmer of phantom lakes and floating cities, nature's own lessons in the art of making reality bend and dance before your wondering eyes. In laboratories around the world, scientists work like master craftsmen at scales so small that their tools can place individual atoms exactly where they want them. They are building materials that nature never imagined, structures so tiny and precise that they can teach light entirely new ways to behave. These artificial materials are called metamaterials, meaning beyond materials. They do not follow the usual rules that govern how substances interact with light. Instead, they create their own rules, written in arrangements of metal and plastic smaller than the wavelength of light itself. Imagine trying to build a house for creatures that are smaller than the bricks you are using. This is the challenge that scientists face when creating metamaterials. Light waves are already incredibly small, but the structures needed to control them must be even smaller. A typical metamaterial looks like a flat sheet of plastic or glass covered with patterns that repeat over and over. These patterns might be tiny rings or split circles or geometric shapes that look like abstract art. Each pattern is carved with precision that makes the finest watchmaking seem crude by comparison. When light encounters one of these patterned surfaces, something remarkable happens. The light does not simply bounce off or pass through. Instead, it interacts with each tiny structure individually. Thousands or millions of these interactions happen simultaneously, creating effects that seem to violate the basic laws of physics. Some metamaterials can bend light backwards in directions that natural materials never could. Others can slow light down to the speed of a walking person or speed it up beyond what should be possible. The most exotic ones can make light appear to flow around objects as if those objects were not there at all. The secret lies in the precise size and shape of each tiny structure. Scientists must calculate exactly how each piece will affect light waves, then arrange millions of these pieces in perfect patterns. It is like composing a symphony where each note is smaller than anything the human eye can see. Creating these materials requires tools that seem almost magical themselves. Electron beam machines can carve patterns into metal films with precision measured in nanometers. That is smaller than a virus, smaller than the wavelengths of visible light, smaller than anything your eyes could ever hope to see directly. Other techniques use light itself to write patterns into special materials. Scientists shine carefully controlled laser beams on surfaces coated with light-sensitive chemicals. Where the light hits, the chemical changes, leaving behind permanent patterns that can guide other light waves. The most advanced metamaterials are built in layers, like microscopic skyscrapers. Each layer has its own pattern, designed to work together with the layers above and below. The result is a three-dimensional maze that guides light through predetermined pathways. These layered structures can create effects that change depending on which direction you view them from. A metamaterial might be completely transparent when you look at it from one angle, but perfectly reflective when you view it from another angle. The material itself never changes, but its interaction with light creates these shifting properties. Some metamaterials respond to external signals. Apply electricity, and their optical properties change instantly. Shine a laser on them, and they switch from transparent to opaque. Heat them up, and they might begin bending light in completely different directions. These responsive materials open possibilities for invisibility cloaks that could be turned on and off at will. The challenge of making metamaterials work in the real world goes beyond just building tiny structures. The materials must be durable enough to survive outside the laboratory. They must work in sunlight, in rain, and temperature changes. They must be flexible enough to wrap around curved objects while maintaining their precise optical properties. Scientists have created metamaterials that work with specific colors of light. A material might be perfectly designed for red light, but have no effect on blue light. Creating materials that work with all colors simultaneously requires even more complex structures, with multiple patterns overlapping and interacting. The first metamaterials only worked with microwaves, the same type of radiation used in microwave ovens and radar systems. These longer wavelengths are easier to manipulate because the structures needed to control them can be larger and easier to manufacture. As scientists learned to work at smaller and smaller scales, they began creating metamaterials for infrared light, the heat radiation that your body gives off. These materials could hide objects from heat-seeking sensors, making them invisible to night vision equipment while remaining visible to normal eyesight. The ultimate goal is metamaterials that work with all wavelengths of visible light simultaneously. Such materials would need structures that are organized at multiple scales, from the nanometer level up to the micrometer level. Each scale would handle different wavelengths of light, working together to create perfect optical control. Some metamaterials achieve their effects through resonance, the same principle that allows a singer to shatter a wine glass by hitting exactly the right note. The tiny structures in the metamaterial are designed to resonate at specific light frequencies, amplifying certain colors while suppressing others. Other metamaterials work by creating artificial magnetic responses to light. Normal materials do not have strong magnetic interactions with light waves, but carefully designed metamaterial structures can create these interactions artificially. This opens up entirely new possibilities for controlling light behavior. The mathematics behind metamaterial design involves solving complex equations that describe how electromagnetic waves interact with tiny structures. Scientists use powerful computers to model millions of possible designs, searching for arrangements that will produce the desired optical effects. Manufacturing metamaterials requires cleanroom facilities that are more sterile than hospital operating rooms. Even tiny particles of dust can ruin the delicate structures. Workers must wear special suits and follow strict procedures to prevent contamination during the fabrication process. As the field advances, scientists are developing new ways to mass-produce metamaterials. Instead of carving each structure individually, they're learning to print entire metamaterial sheets using techniques borrowed from computer chip manufacturing. This could make these exotic materials practical for everyday use. The applications of metamaterials extend far beyond invisibility cloaks. They could revolutionize solar panels by capturing light more efficiently. They could improve medical imaging by focusing light and other waves with unprecedented precision. They could enable new types of optical computers that process information using light instead of electricity. Some researchers are exploring metamaterials that can manipulate sound waves as well as light waves. These acoustic metamaterials could create cloaks that hide objects from sonar or materials that can channel sound in impossible directions. The boundary between science fiction and science fact continues to blur as metamaterial research advances. Materials that can bend space itself, lenses that can see through walls, surfaces that can become perfectly black or perfectly reflective on command. All of these possibilities emerge from the precise arrangement of structures smaller than light itself. As you rest tonight, surrounded by ordinary materials that follow nature's ancient rules, imagine the laboratories where scientists continue their patient work, building tomorrow's impossible materials one atom at a time, teaching light to dance in ways it has never danced before. Imagine light as a vast orchestra playing an infinite symphony. Each instrument represents a different frequency of light, from the deep, slow notes of radio waves to the high, quick vibrations of gamma rays. Your eyes can hear only a tiny portion of this cosmic concert, the narrow range of frequencies you call visible light. Red light vibrates about 430 trillion times per second. Blue light dances almost twice as fast, at about 750 trillion vibrations per second. Between these extremes lie all the colors of the rainbow, each singing its own frequency song as it travels through space. But the symphony extends far beyond what your eyes can perceive. Below the deep red notes lie infrared frequencies, the warm radiation that your skin can feel as heat. Above the highest blue notes stretch ultraviolet frequencies, the invisible light that can burn your skin on sunny days. Each frequency of light behaves slightly differently when it encounters matter. This is why a prism can split white light into rainbows. The glass bends blue light more sharply than red light, separating the frequencies that were traveling together as white light. This frequency-dependent behavior is crucial for understanding how invisibility cloaks work in the real world. A cloak that perfectly hides an object from red light might have no effect at all on blue light. The object would appear to change color as you looked at it, revealing the presence of the cloak. Scientists working on invisibility technology must choose which frequencies to target. Do they design their cloak to work with visible light, making objects disappear to human eyes? Or do they focus on infrared frequencies, hiding objects from heat-seeking cameras and sensors? Military applications often prioritize infrared cloaking. Many detection systems rely on the heat signatures that all warm objects emit. A tank might be perfectly visible to your eyes, but completely invisible to infrared sensors if it is wrapped in the right frequency-specific cloak. The challenge becomes even more complex when scientists try to create cloaks that work across multiple frequencies simultaneously. Each frequency requires its own specific arrangement of metamaterial structures. Creating a cloak that works for both red and blue light means designing structures that can handle both frequencies without interference. Some of the most successful invisibility demonstrations have focused on microwave frequencies, the same radiation used in radar systems. These longer wavelengths are easier to manipulate because the metamaterial structures needed to control them can be larger and simpler to manufacture. At microwave frequencies, scientists have successfully hidden objects completely from radar detection. A metal cylinder wrapped in the right metamaterial becomes invisible to radar waves, as if it were not there at all. The radar waves flow around the hidden object and continue on their path, carrying no information about what they passed. But scaling these successes to visible light frequencies presents enormous challenges. The metamaterial structures must become thousands of times smaller while maintaining the same precise control over light behavior. It is like trying to build a watch using tools designed for constructing buildings. Infrared cloaking represents a middle ground between the relative ease of microwave cloaking and the extreme difficulty of visible light cloaking. Infrared light has wavelengths longer than visible light, but shorter than microwaves, making the required metamaterial structures challenging but not impossible to create. Your own body is constantly emitting infrared radiation. Your skin temperature of about 98 degrees Fahrenheit causes you to glow brightly in infrared light, even though you appear perfectly normal to visible light. An infrared camera can see you clearly in complete darkness, detecting the heat signature you cannot hide. Some animals have evolved natural infrared detection abilities. Certain snakes can sense the body heat of their prey using special organs that detect infrared radiation. To these snakes, warm-blooded animals glow like bright lights against the cooler background, making them easy to hunt even in darkness. Scientists have created materials that can manipulate infrared light in remarkable ways. Some can make hot objects appear cold to infrared cameras. Others can redirect infrared radiation around objects, creating infrared shadows where logic says there should be none. The frequency selectivity of invisibility cloaks creates interesting possibilities for partial concealment. A cloak might hide an object completely in infrared while leaving it fully visible to normal eyesight. This could allow soldiers to move unseen by heat-seeking sensors while remaining visible to their human allies. Different materials have different relationships with various frequencies of light. Glass is transparent to visible light, but opaque to most infrared frequencies. Water absorbs certain infrared wavelengths strongly while allowing others to pass through freely. Understanding these frequency-dependent properties is crucial for cloak design. The atmosphere itself acts as a frequency-selective filter. Some infrared frequencies pass through air easily, while others are absorbed by water vapor and carbon dioxide. This natural filtering affects how infrared cloaking systems work in real-world conditions outside the laboratory. Scientists have discovered that the same metamaterial structure can have completely different effects on different frequencies of light. A pattern that creates perfect invisibility for infrared light might actually enhance visibility for blue light, making objects appear brighter rather than hiding them. This frequency dependence leads to some of the most beautiful effects in invisibility research. Objects wrapped in frequency-selective cloaks can appear to shimmer and change as they are viewed under different types of light. They might vanish under infrared illumination while remaining perfectly visible under normal lighting conditions. The human eye's limited frequency range becomes an advantage in some invisibility applications. A cloak that works only in the ultraviolet range would be invisible to human observers, but easily detectable by cameras designed to see ultraviolet light. This creates possibilities for steganography, hiding messages or objects in frequencies that human eyes cannot perceive. Future invisibility cloaks might work by frequency division, hiding different parts of an object at different frequencies. The result would be objects that appear fragmented or ghostly when viewed through cameras that can see multiple frequency ranges simultaneously. Some researchers are exploring dynamic frequency cloaking, materials that can shift their invisibility from one frequency range to another in response to electrical signals. Such cloaks could adapt to different detection threats, switching from infrared concealment to visible light concealment as needed. The physics of frequency-dependent invisibility reveals something profound about the nature of reality itself. What you see is solid. Permanent objects are actually complex interactions between matter and specific frequencies of electromagnetic radiation. Change the frequency, and you change what can be seen. As you prepare for sleep tonight, consider the invisible symphony playing all around you. Radio waves carry distant music through your room. Infrared radiation flows from your warm body into the cooler air. Cosmic rays from distant stars pass through the walls as if they were not there at all. And in laboratories around the world, scientists continue learning to conduct this invisible orchestra, teaching each frequency to dance around hidden objects in its own unique way. Every step you take is accompanied by a silent partner that never leaves your side. Your shadow stretches and shrinks as you move through the day, a dark mirror of your actions painted on walls, sidewalks, and grass. But what if this faithful companion could be taught to disappear? Your shadow exists because your body blocks light from reaching the surface behind you. Light travels in straight lines, and when your solid form stands in its path, it creates a region of darkness shaped exactly like your silhouette. This seems like one of the most basic, unchangeable facts of the physical world. Yet scientists have discovered ways to make shadows vanish, to fill in the darkness with carefully crafted light. The technique sounds almost too simple to believe. They use additional light sources to illuminate the shadowed areas, matching the brightness and color of the surrounding regions so perfectly that the shadow disappears. Imagine standing in bright sunlight with your shadow clearly visible on the ground behind you. Now imagine a second light source, positioned carefully to shine light exactly where your shadow falls. If this second light is perfectly calibrated, it can fill in your shadow completely, making it appear as if you cast no shadow at all. This shadow cancellation requires extraordinary precision. The additional light must match not only the brightness of the surrounding area, but also its exact color and direction. Even tiny differences become visible to careful observers, revealing the artificial nature of the illumination. The challenge becomes more complex when multiple light sources create multiple shadows. Stand under several lights, and you cast several shadows in different directions. Canceling all of these shadows simultaneously requires sophisticated systems that can track your movement and adjust multiple light sources in real time. Scientists have created laboratory demonstrations where objects appear to float without casting shadows. A ball suspended in midair looks as if it defies gravity because the expected shadow beneath it simply is not there. The effect is so convincing that it can fool even trained observers who know exactly how the trick is accomplished. These shadow-canceling systems work best with controlled lighting conditions. In a laboratory or studio, where scientists can control every light source, perfect shadow cancellation is possible. But outdoors, under the sun, the challenge becomes far more difficult. Sunlight creates hard, sharp shadows because the sun acts like a single, very bright point of light source. To cancel a shadow created by sunlight, you would need an artificial light source almost as bright as the sun itself, positioned to shine from the exact opposite direction. Some researchers have experimented with arrays of many smaller lights instead of single bright sources. These arrays can create more diffuse illumination that matches the scattered light of an overcast day. Under these conditions, shadow cancellation becomes more practical, though still technically demanding. The human visual system makes shadow cancellation both easier and harder than it might seem. Your eyes and brain are remarkably good at detecting subtle differences in lighting, making it difficult to fool human observers with imperfect shadow cancellation. But your visual system also makes assumptions about lighting that can sometimes be exploited. Your brain expects shadows to exist. When you see an object, you unconsciously look for a shadow to help judge the object's position in relationship to its surroundings. Remove the shadow, and the object can appear to float or seem disconnected from the physical world around it. This expectation creates opportunities for illusion. Objects that cast no shadow often appear lighter, more ethereal, as if they were made of different material than expected. The absence of shadow changes not just how the object looks, but how substantial it feels to observers. Stage magicians and theatrical lighting designers have long understood these principles. By carefully controlling shadows, they can make objects appear and disappear, seem to float, or look more or less solid than they really are. Professional lighting can transform the appearance of people and objects through shadow manipulation alone. Modern projection systems offer new possibilities for shadow cancellation. Instead of using fixed light sources, projectors can create patterns of light that change instantly. A projector could track moving objects and continuously project light patterns that cancel their shadows in real time. This dynamic shadow cancellation could work with moving people and objects. As you walk through a space equipped with shadow-canceling projectors, the system would track your movement and continuously eliminate your shadow, creating the illusion that you cast no shadow at all. Some of the most advanced research combines shadow cancellation with other invisibility techniques. A partial invisibility cloak might make an object nearly transparent, while shadow-canceling systems eliminate the remaining shadow. The combination could create more complete concealment than either technique alone. The physics of shadow cancellation reveals something fundamental about light itself. Light waves can add together, creating brighter regions where waves reinforce each other. They can also cancel each other out in certain circumstances, creating darker regions where waves interfere destructively. This wave behavior of light is the same principle behind noise-canceling headphones. Just as those headphones create sound waves that cancel unwanted noise, shadow-canceling systems create light waves that cancel unwanted darkness. Water demonstrates similar shadow effects that scientists study for inspiration. Underwater, shadows behave differently because water scatters and absorbs light. Fish often appear to have softer, less defined shadows that fade gradually into the surrounding water rather than creating sharp edges. This underwater lighting environment provides clues for creating more natural-looking shadow cancellation. Instead of completely eliminating shadows, some systems create softer, more diffuse shadows that look more natural while still reducing the visual impact of the hidden object. Artists have long used understanding of light and shadow to create illusions on canvas. Painters can make flat surfaces appear three-dimensional by carefully controlling where they place highlights and shadows. Shadow-canceling technology applies these same principles using real light instead of paint. The psychological impact of missing shadows can be surprisingly strong. People often feel unsettled when viewing objects that cast no shadow, even when they cannot consciously identify what seems wrong. The absence of shadow creates a subtle but persistent sense that something is not quite right with the scene. This psychological response suggests that shadow canceling could be effective for creating invisibility even when the cancellation is not perfect. Objects with significantly reduced shadows often go unnoticed by casual observers, even when the objects themselves remain clearly visible. Future shadow canceling systems might use artificial intelligence to predict where shadows should fall and automatically generate the light patterns needed to cancel them. These smart systems could work in complex, changing lighting conditions without requiring manual calibration. The combination of shadow cancellation with adaptive camouflage could create remarkably effective concealment. An object that matches its background color while casting no shadow would be very difficult to detect, especially for moving observers who do not have time to examine scenes carefully. As you settle into the growing darkness of evening, notice how shadows begin to soften and merge. The harsh shadows of daylight fade into the gentle gradations of twilight, where light and darkness blend together like watercolors running on wet paper. And perhaps in your dreams tonight, you will walk through a world where shadows have learned to hide themselves, where darkness itself has become invisible. Imagine a world where objects exist in multiple places at the same time. A world where the simple act of looking at something changes its nature. A world where particles can tunnel through walls as if those walls were made of mist. This is not a fantasy realm, but the very real quantum world that exists at the smallest scales of reality. At the level of atoms and electrons, the familiar rules of the everyday world no longer apply. Particles behave more like ghostly possibilities than solid objects. They exist in states of maybe, perhaps, and could be, rather than the definite here and now of your ordinary experience. This strange quantum realm offers new inspiration for invisibility research. While large objects like people and cars must follow the predictable laws of classical physics, tiny particles follow quantum rules that seem to allow for impossible behaviors, including forms of natural invisibility. Consider an electron orbiting an atomic nucleus. Unlike a planet orbiting the sun, this electron does not follow a single, predictable path. Instead, it exists as a cloud of probability, spread out around the nucleus in regions where it might be found if someone were to look for it. The electron is not traveling along all these paths simultaneously. It exists in what quantum physicists call a superposition, a state where all possibilities coexist until the moment of observation collapses them into a single reality. This is nature's own form of invisibility, where particles hide by existing everywhere and nowhere at once. When scientists try to observe these quantum particles directly, something remarkable happens. The act of observation itself forces the particle to choose a definite location. Before observation, the particle existed as a spread-out possibility. After observation, it becomes a point-like reality in a specific place. This observer effect suggests a profound connection between consciousness, measurement, and physical reality. The quantum world seems to know when it is being watched, responding by abandoning its ghostly superposition states and behaving more like the solid, predictable objects of everyday experience. Quantum tunneling offers another window into nature's invisibility tricks. Sometimes, quantum particles can pass through barriers that should be impossible to cross. An electron might encounter a wall of energy that classical physics says it cannot penetrate. Yet quantum mechanics allows it to appear on the other side, as if the wall were not there. This tunneling happens because quantum particles are not truly solid objects, but rather wave-like disturbances in quantum fields. When a wave encounters a barrier, part of it can extend beyond the barrier, even when most of it is reflected back. If the barrier is thin enough, the wave can emerge on the far side, carrying the particle with it. Scientists have observed quantum tunneling in many contexts. Electrons tunnel through the barriers in computer chips, enabling modern electronics to function. Particles tunnel through barriers in radioactive decay, allowing atomic nuclei to emit radiation even when they lack the energy to break apart through classical means. Some researchers wonder whether quantum tunneling might be scaled up to create macroscopic invisibility effects. If large objects could somehow be convinced to behave like quantum particles, they might be able to tunnel through barriers or exist in superposition states that make them effectively invisible. The challenge lies in maintaining quantum behavior at larger scales. Quantum effects are incredibly fragile. They disappear almost instantly when particles interact with their environment through processes that physicists call decoherence. The warm, noisy world of everyday experience destroys quantum superpositions faster than they can be observed. Yet scientists have succeeded in creating quantum effects in increasingly large systems. They have put molecules into superposition states. They have created quantum entanglement between objects visible to the naked eye. Each success suggests that the boundary between quantum and classical behavior might be more flexible than once believed. Quantum entanglement offers perhaps the most mysterious connection to invisibility research. When two particles become quantum entangled, they share a single quantum state regardless of how far apart they might be. Measuring one particle instantly affects the other, as if they remain connected by invisible threads. Einstein called this effect spooky action at a distance, because it seemed to violate the principle that nothing can travel faster than light. Yet experimental tests have confirmed that quantum entanglement is real. The connection between entangled particles appears to operate outside the normal limitations of space and time. Some researchers speculate about using quantum entanglement to create perfect invisibility cloaks. If light could be entangled with the object it illuminates, then measuring the light might reveal information about the object's state without the light ever directly interacting with the object. The object could remain hidden while its quantum twin reveals its presence. The quantum world also challenges our understanding of what it means to be invisible. In classical physics, invisibility means that light passes around or through an object without being affected by it. In quantum physics, the boundary between object and light becomes blurred. Quantum fields fill all of space, creating a background of virtual particles that constantly appear and disappear. These virtual particles are not directly observable, yet they have measurable effects on real particles and light. They represent a kind of quantum invisibility, where unobservable entities influence observable reality. Scientists have discovered that empty space itself is not truly empty, but filled with quantum fluctuations. These fluctuations create measurable forces between objects, push apart parallel metal plates, and contribute to the energy of the universe. They are invisible in the sense that they cannot be directly observed, yet their effects permeate everything. Some quantum effects create natural cloaking behaviors. Certain materials can enter quantum states where they become transparent to specific types of light. Others can create quantum interference patterns that cancel out their visibility under particular conditions. The study of quantum invisibility has led to practical applications in quantum computing and quantum communication. Quantum computers use superposition states to perform calculations that would be impossible for classical computers. Quantum communication systems use entanglement to create unbreakable codes. These quantum technologies work precisely because they exploit the invisible aspects of quantum reality. Information can be processed in superposition states that cannot be directly observed. Messages can be transmitted through entangled particles that share invisible connections across vast distances. The mathematics of quantum mechanics describes reality in terms of probability waves rather than definite objects. These waves can interfere with each other, creating patterns of reinforcement and cancellation similar to the interference patterns created by water waves or sound waves. When quantum probability waves interfere destructively, they can create regions where the probability of finding a particle becomes zero. In these regions, the particle is effectively invisible, not because it has moved somewhere else, but because the mathematics of quantum mechanics forbids it from existing there. The philosophical implications of quantum invisibility extend far beyond physics. If fundamental particles can exist in multiple places simultaneously, if observation creates reality rather than merely revealing it, if empty space is filled with invisible influences, then what does it mean for anything to be truly visible or invisible? These questions touch on the deepest mysteries of existence itself. The quantum world suggests that reality is far stranger and more subtle than everyday experience reveals. It hints at levels of existence that remain forever hidden behind veils of uncertainty and probability. As you drift toward sleep tonight, consider that your body is composed of countless quantum particles, each existing in its own cloud of possibility. Every atom within you participates in the quantum dance of superposition and collapse, creating the solid reality of your being from the ghostly mathematics of probability. And perhaps in dreams, where the normal rules of physics bend and break, you touch something closer to the quantum reality that underlies all visible things. Every morning, when you look into a mirror, you see a faithful companion staring back at you. The mirror speaks only truth, reflecting light with perfect honesty. Every photon that strikes its surface bounces back at precisely the same angle it arrived, following laws as reliable as sunrise. But what if mirrors could be taught to lie? What if their reflections could show you things that are not there, or hide things that are? Scientists have discovered that by arranging mirrors in clever ways, they can create optical illusions so convincing that solid objects appear to vanish completely. The simplest mirror magic uses the predictable behavior of reflected light. When light hits a mirror, it follows a rule so simple that ancient Greek mathematicians could describe it perfectly. The angle of incidence equals the angle of reflection. Light coming in at 30 degrees bounces out at 30 degrees every time without exception. This unwavering reliability makes mirrors powerful tools for controlling light. Unlike materials that absorb, scatter, or bend light in complex ways, mirrors redirect light along paths that can be calculated precisely. Scientists can predict exactly where every reflected ray will go, making mirrors ideal for creating controlled optical illusions. Imagine a simple box with a mirror placed diagonally inside it. When you peer into the box from above, the mirror reflects light from the sidewalls, making them appear to be the bottom of the box. The real bottom disappears from view, hidden behind the mirror's reflection. The box appears to be half as deep as it really is. This is the foundation of mirror-based invisibility. By hiding parts of objects behind reflections of other parts, mirrors can make objects appear to have different shapes than they actually do. With careful planning, they can make parts of objects disappear entirely. The most elegant mirror invisibility systems use arrays of many small mirrors, each one positioned to reflect light from a specific direction. These arrays can create the illusion that you're looking straight through a solid object, seeing whatever lies behind it instead of the object itself. Consider a simple demonstration that researchers have built in laboratories around the world. A box sits on a table, but mirrors arranged around its base reflect images of the table's surface from behind the box. To observers in front, it appears as if they can see straight through the box to the table beneath. The box seems to hover in midair. This technique works because your eyes and brain make assumptions about what they see. When light appears to come from behind an object, your visual system interprets this as evidence that the object is transparent. The mirrors exploit these assumptions, feeding your eyes information that creates false conclusions. More sophisticated mirror systems can work from multiple viewing angles simultaneously. By using curved mirrors or complex arrangements of flat mirrors, researchers can create illusions that remain convincing even as observers move around the hidden object. The mirrors continuously redirect light to maintain the transparency illusion. The challenge with mirror-based invisibility lies in achieving perfect alignment. Each mirror must be positioned with extraordinary precision to reflect light from exactly the right direction. Even tiny errors in mirror placement can create visible distortions that reveal the presence of the hidden object. Scientists have developed computer-controlled mirror systems that can adjust their positions automatically. These adaptive systems use cameras to monitor the optical illusion in real time, making tiny corrections to maintain perfect invisibility as lighting conditions change or as observers move to different positions. Some of the most impressive mirror invisibility demonstrations use retroreflectors, special mirror arrangements that reflect light directly back toward its source regardless of the angle at which it arrives. These retroreflectors are the same technology used in bicycle reflectors and road signs that glow brightly in headlight beams. By covering an object with retroreflectors and illuminating it with light from the observer's direction, researchers can make the object appear to glow with the same brightness and color as its surroundings. The retroreflectors send back light that matches what should be coming from behind the object, creating a convincing transparency effect. The bicycle wheel invisibility demonstration has become famous in scientific circles. Researchers mount retroreflectors around the rim of a bicycle wheel, then illuminate the wheel with light positioned near the observer's eyes. The retroreflectors make the wheel appear transparent, creating the illusion of a bicycle with no wheel. Mirror systems can also create active camouflage by displaying images on screens positioned where mirrors might normally be placed. Cameras capture images of what lies behind the object, and screens display these images to observers in front. The result is real-time transparency that adapts to changing conditions. Military researchers have experimented with mirror-based camouflage systems for vehicles and aircraft. By covering surfaces with precisely angled mirrors, they can reflect images of the sky or ground, making vehicles blend into their surroundings when viewed from specific angles. The optical properties of mirrors make them nearly perfect for certain invisibility applications. Unlike metamaterials or other exotic technologies, mirrors work across all frequencies of visible light simultaneously. A mirror-based invisibility system that works for red light will also work for blue light, green light, and every other color. However, mirror systems have significant limitations. They typically work well only from specific viewing angles. Move too far to one side, and the illusion breaks down as the mirrors begin reflecting light from the wrong directions. Creating mirror systems that work from all angles requires complex three-dimensional arrangements of curved mirrors. The reflective surfaces must also remain perfectly clean and undamaged to maintain their optical properties. Dust, scratches, or condensation on mirrors can scatter light in unwanted directions, creating visible artifacts that reveal the presence of the invisibility system. Some researchers combine mirrors with other technologies to overcome these limitations. Mirrors might handle the primary invisibility effect, while other systems deal with secondary effects like shadows or thermal signatures. The combination can be more effective than any single technology alone. The psychology of mirror-based invisibility reveals interesting aspects of human perception. People often notice something is unusual about mirror-based illusions, even when they cannot identify exactly what is wrong. The brain seems to have subtle mechanisms for detecting optical inconsistencies that challenge mirror camouflage systems. Artists and stage magicians have long understood the power of mirrors to create impossible-seeming effects. The classic disappearing lady trick uses mirrors to make a person appear to vanish from a cabinet. The lady is still there, but mirrors redirect light to create the illusion of empty space. Modern digital technology has opened new possibilities for mirror-based invisibility. Electronic mirrors that can change their reflective properties on command could create adaptive camouflage systems. These smart mirrors could switch between different reflection patterns to maintain invisibility under changing conditions. As you prepare for sleep tonight, notice your reflection in the darkened window beside your bed. See how the glass acts as a partial mirror, showing you a ghostly version of yourself superimposed on the world outside. And perhaps in your dreams, you will discover mirrors that reflect not what is, but what every dream of invisibility eventually meets the patient reality of physical laws. Like a gentle teacher, physics whispers the boundaries that even the most perfect invisibility cloak cannot cross. These limits are not failures of imagination or engineering, but fundamental truths about how light, matter, and observation work together in our universe. The most basic challenge facing any invisibility cloak is the problem of multiple observers. Imagine trying to hide from two people standing in different places at the same time. Light that appears to come from behind you when viewed from the first person's position must somehow also appear to come from behind you when viewed from the second person's position. This seems simple until you realize that these two observers see you from different angles. The light reaching their eyes travels along completely different paths. A cloak that perfectly guides light around you for the first observer might send entirely wrong information to the second observer, revealing your presence rather than hiding it. The challenge multiplies as more observers are added. Hide from 3 people, then 4, then a dozen. Each additional observer requires the cloak to handle light from another unique direction. The mathematical complexity grows exponentially, demanding increasingly sophisticated solutions. Moving observers create even greater challenges. As someone walks around your cloak position, their perspective constantly changes. The cloak must continuously adjust how it handles light to maintain the illusion of invisibility from every angle along the observer's path. This dynamic adaptation requires incredible precision and speed. Your own movement while cloaked introduces another layer of complexity. As you walk, the background that the cloak must simulate changes continuously. A perfect cloak would need to project accurate images of whatever lies behind you at every moment, updating these images in real time as your position shifts. The bandwidth problem poses another fundamental limit. Your eyes can distinguish millions of different colors, each representing light at a specific frequency. A perfect invisibility cloak must handle all these frequencies simultaneously, guiding each one along its own precise path around your body. But light carries more information than just color. It also carries information about polarization, the orientation of the light waves as they travel through space. Polarized sunglasses work by blocking light waves oriented in specific directions. A complete invisibility cloak must preserve not just the color of light, but also its polarization state. The speed of light itself creates constraints on invisibility systems. Light travels very fast, but not infinitely fast. When an observer moves, or when lighting conditions change, there's a brief delay before a responsive invisibility system can adapt. During this delay, imperfections in the illusion might become visible to careful observers. Quantum mechanics introduces its own subtle limits on perfect invisibility. The act of measuring light to determine what should be projected by an active camouflage system necessarily disturbs the light being measured. This quantum uncertainty means that perfect reproduction of light patterns may be fundamentally impossible. The conservation of energy places firm boundaries on what invisibility systems can accomplish. Light carries energy, and energy cannot be created or destroyed, only transformed from one form to another. A cloak that redirects light must account for where that light energy goes and ensure that energy balance is maintained. Heat generation becomes a practical problem for many invisibility technologies. Metamaterials that manipulate light often convert some of that light energy into heat. This waste heat must be dissipated somehow, and getting rid of heat without creating detectable thermal signatures presents its own engineering challenges. The resolution limit of any optical system constrains how perfectly invisibility can be achieved. Just as cameras have limited resolution, human eyes cannot detect details smaller than a certain size. This fundamental limit means that perfect invisibility may only need to be perfect down to the scale of human visual perception. Atmospheric effects introduce real-world complications that laboratory demonstrations often ignore. Air turbulence scatters light in random directions. Humidity absorbs certain wavelengths more than others. Pollution particles in the air create additional scattering that can reveal the presence of objects that should be invisible. The weight and size of invisibility systems create practical constraints. A cloak made of heavy metamaterials might render someone invisible but immobile. Battery-powered active camouflage systems must balance invisibility performance against power consumption and battery life. Manufacturing tolerances set limits on how precisely invisibility devices can be built. Even tiny imperfections in the construction of metamaterials can create visible artifacts. The more perfect the invisibility effect needs to be, the more precisely the system must be manufactured, driving up costs and complexity. Environmental durability challenges invisibility systems designed for real-world use. Laboratory demonstrations often work under controlled conditions with stable lighting and temperature. Outside the laboratory, invisibility systems must continue working despite rain, dust, temperature changes, and mechanical vibrations. The psychological limits of human perception create interesting boundaries for invisibility research. People are remarkably good at detecting when something looks wrong, even if they cannot identify exactly what seems off. Perfect invisibility might require fooling not just conscious perception, but also subconscious pattern recognition systems in the brain. Some physical limits may be more flexible than they initially appear. What seems impossible with current technology might become achievable as new materials, manufacturing techniques, and computational methods are developed. The boundaries between possible and impossible continue to shift as science advances. Other limits appear to be truly fundamental, arising from the basic structure of reality itself. These absolute limits come from the laws of thermodynamics, the principles of quantum mechanics, and the geometry of space-time. No amount of technological advancement can overcome constraints that are built into the fabric of the universe. The interaction between different physical phenomena creates compound limitations that are more restrictive than any single constraint. A system that solves the multiple observer problem might create new thermal signature problems. A solution to the bandwidth challenge might introduce manufacturability issues. Research into invisibility limits has practical value beyond the development of cloaking technology. Understanding why certain things are impossible often reveals why other things might be possible. The boundaries of the impossible map out the territory of the achievable. Some researchers focus specifically on these fundamental limits, seeking to understand exactly what physics allows and forbids. Their work helps guide practical invisibility research by identifying which approaches have theoretical promise and which face insurmountable obstacles. The history of technology shows that apparent limits are sometimes overcome by creative approaches that circumvent rather than violate physical constraints. Flight was impossible until the Wright brothers found a way to generate lift. Space travel was impossible until rockets learned to carry their own oxidizer. Perhaps perfect invisibility will always remain impossible, constrained by the immutable laws of physics. Or perhaps future researchers will discover clever workarounds that achieve practical invisibility without violating any fundamental principles. The gentle boundaries that physics sets around our dreams continue to guide us toward understanding what might truly be possible. As you settle into the quiet darkness of approaching sleep, consider how even your resting body operates within physical limits. Your heartbeat constrained by the properties of muscle and blood, your breathing governed by the chemistry of oxygen and carbon dioxide. Yet within these gentle boundaries, the remarkable complexity of life flourishes, suggesting that perhaps the most beautiful possibilities emerge not despite physical limits, but because of the creative spaces they define. Your eyes are remarkable instruments, capable of distinguishing millions of colors and detecting single photons that have traveled across the universe. Yet for all their sensitivity and precision, they perceive only the tiniest fraction of the electromagnetic radiation that surrounds you every moment of your life. The light you see, from deep red to brilliant violet, spans wavelengths from about 700 to 380 nanometers. This narrow band represents less than 1% of all electromagnetic radiation. You live in a vast ocean of invisible light, aware of only the shallow waters near the shore. Just beyond the red edge of your vision lies infrared radiation, the gentle warmth you feel from sunlight on your skin. Your body constantly radiates infrared light, glowing like a beacon to creatures and instruments that can see in these longer wavelengths. Every breath you take, every heartbeat, every thought creates patterns in this invisible radiance. Snakes can see infrared light through special organs that detect heat signatures. To a rattlesnake, you appear as a brilliant figure of warmth against the cooler background of the world around you. Your body temperature of 98.6 degrees Fahrenheit makes you shine like a star in their heat-sensitive vision. Military night vision systems reveal this hidden world of thermal radiation. Through infrared cameras, a warm cup of coffee glows brightly even in complete darkness. Your footprints remain visible on cold pavement long after you have passed, each step leaving a brief thermal shadow of your presence. Beyond the violet edge of your vision lies ultraviolet light, radiation energetic enough to break chemical bonds and cause sunburns. Flowers that appear uniformly colored to your eyes often display intricate patterns when viewed in ultraviolet light. These hidden designs serve as landing strips for bees and other pollinators whose eyes can see ultraviolet wavelengths. Many birds can see ultraviolet light, revealing a visual world far richer than anything humans can naturally perceive. Male and female birds that appear identical to your eyes often display dramatic differences in ultraviolet coloration. Their feathers carry secret messages written in wavelengths you cannot read. The challenge for invisibility research lies in hiding from all these invisible forms of detection simultaneously. A cloak that makes you vanish from human sight might leave you perfectly visible to infrared cameras, ultraviolet sensors, or the heat-detecting organs of hunting snakes. Creating broad-spectrum invisibility requires understanding how different wavelengths interact with materials in different ways. Glass that is transparent to visible light often blocks ultraviolet and infrared radiation. Water absorbs infrared light strongly while allowing visible light to pass through relatively freely. These wavelength-dependent properties mean that invisibility cloaks must be designed differently for different regions of the electromagnetic spectrum. A metamaterial that bends visible light around an object might have completely different effects on infrared radiation passing through the same space. Some invisibility research focuses specifically on infrared concealment because thermal detection is so widely used in security and military applications. Hiding your heat signature requires either cooling your body to match the surrounding temperature or redirecting your thermal radiation away from potential observers. Specialized materials can manipulate infrared light in ways that seem almost magical. Some can make hot objects appear cold to thermal cameras. Others can redirect thermal radiation around objects, creating infrared shadows that hide the heat signatures of whatever lies within them. Ultraviolet invisibility presents its own unique challenges. The shorter wavelengths of ultraviolet light interact more strongly with many materials, making them harder to manipulate using conventional optical techniques. The high energy of ultraviolet photons can also damage the materials used to build invisibility systems. Radio waves represent the longest wavelengths that scientists commonly work with for invisibility research. These wavelengths are so long that the structures needed to manipulate them can be built using conventional manufacturing techniques. Radio wave cloaking was among the first successful invisibility demonstrations. At radio frequencies, researchers have created cloaks that completely hide objects from radar detection. Fighter aircraft use stealth technology based on similar principles, using special shapes and materials to scatter radar waves away from their sources rather than reflecting them back. X-rays occupy the short wavelength end of the electromagnetic spectrum, carrying so much energy that they can pass through soft tissues while being blocked by denser materials like bones and metals. X-ray invisibility would require materials that can manipulate these highly energetic photons without being damaged by them. The atmosphere itself acts as a selective filter for different wavelengths of electromagnetic radiation. Visible light passes through air easily, but many infrared wavelengths are absorbed by water vapor and carbon dioxide. This natural filtering affects how invisibility cloaks work in real-world environments. Some wavelengths of electromagnetic radiation come from space, carrying information about distant stars and galaxies. Radio telescopes detect these cosmic signals, searching for patterns that might indicate intelligent life elsewhere in the universe. A perfect invisibility cloak would need to avoid blocking these faint cosmic whispers. The human body interacts differently with different wavelengths of electromagnetic radiation. Visible light reflects off your skin. Infrared radiation is emitted by your warm tissues. Radio waves can pass through your body with minimal interaction. Understanding these interactions is crucial for designing cloaks that can hide human beings effectively. Medical imaging relies on the differential interaction of various electromagnetic wavelengths with biological tissues. X-rays reveal bone structure. Infrared imaging can detect inflammation and blood flow patterns. MRI systems use radio waves to probe the molecular structure of soft tissues. A medical invisibility cloak might selectively hide certain tissues while leaving others visible. Such a device could improve surgical procedures by making overlying tissues transparent to specific wavelengths while maintaining visibility at other wavelengths that surgeons need to see. The development of sensors that can detect multiple wavelengths simultaneously poses new challenges for invisibility research. Modern surveillance systems often combine visible light cameras with infrared sensors and ultraviolet detectors, creating multi-spectral detection capabilities that are harder to fool than single wavelength systems. Scientists are working on adaptive invisibility systems that can adjust their properties across multiple wavelengths in real time. These systems would monitor the electromagnetic environment and automatically optimize their cloaking performance for whatever detection threats are present. The physics of different wavelengths reveals something profound about the nature of reality itself. The electromagnetic spectrum represents a continuous range of phenomena, from radio waves kilometers long to gamma rays smaller than atomic nuclei. Your narrow window of visible perception captures only a tiny sample of this vast continuum. Future invisibility technologies might expand human perception rather than simply hiding objects from existing senses. Imagine contact lenses that could reveal infrared patterns or ultraviolet markings, expanding your natural vision into previously invisible realms of the electromagnetic spectrum. As you rest tonight in the darkness that surrounds your visible world, remember that you are immersed in invisible light of every wavelength, from the warm infrared glow of your own body to the ancient radio waves that have traveled across the cosmos to reach this very spot where you lie. And tomorrow, we will discover how scientists are turning these invisible wonders into tangible realities, bringing the dream of true invisibility closer to the world you can touch and see. In quiet laboratories across the world, scientists hold fragments of tomorrow in their hands. These early invisibility devices are far from perfect, working only under specific conditions, hiding only certain colors of light, functioning for only brief moments. Yet they represent the first tentative steps from dream toward reality. At Duke University, researchers have successfully hidden small objects from microwave radiation using carefully crafted metamaterial cloaks. The hidden objects cast no shadow in microwave light, as if they had stepped out of existence entirely. This proof of concept demonstrates that the physics of invisibility cloaking is not just theoretical, but beautifully, measurably real. In England, scientists have created optical camouflage systems that can hide objects from visible light using arrays of tiny cameras and displays. The cameras capture images of what lies behind the hidden object, while displays project these images to observers in front. The result is a shimmering, ghostly transparency that hints at possibilities beyond current imagination. Japanese researchers have developed materials that can become invisible when viewed from specific angles. By controlling the microscopic structure of surfaces, they guide light around objects in ways that make those objects vanish from certain perspectives. The technology works best with small objects under carefully controlled lighting, but it proves that engineered invisibility is possible. These early successes share common limitations. Most work only with narrow ranges of light frequencies. Some function only from particular viewing angles. Others require enormous amounts of energy or operate only at extremely low temperatures. Yet each breakthrough expands the realm of what might be possible. Military applications drive much of the current research funding. Stealth aircraft already use invisibility principles to avoid radar detection, scattering radio waves away from their sources rather than reflecting them back. These planes represent the first practical invisibility cloaks, albeit ones that work only with specific wavelengths of electromagnetic radiation. The challenge of scaling laboratory demonstrations to real-world applications requires solving countless engineering problems. Materials that work perfectly in controlled laboratory conditions must be made robust enough to function in rain, wind, temperature changes, and mechanical stress. Manufacturing techniques developed for small prototypes must be scaled up to produce larger, more practical devices. Power consumption presents a major obstacle for active invisibility systems. Current prototypes often require more electrical energy than can be practically supplied by portable power sources. Future systems must become far more energy efficient before they can be used outside research facilities. Cost represents another significant barrier. The exotic materials and precision manufacturing required for current invisibility prototypes make them extremely expensive to produce. Only continued research and development can drive these costs down to practical levels for widespread application. Some of the most promising near-term applications focus on narrow, specialized uses rather than general-purpose invisibility. Medical researchers are exploring invisibility techniques that could make surgical instruments transparent to specific wavelengths of light while remaining visible at other wavelengths. This selective invisibility could improve surgical precision and reduce patient trauma. Automotive applications might use invisibility principles to eliminate blind spots in vehicles. Strategic placement of cameras and displays could make parts of a car's structure appear transparent, allowing drivers to see obstacles that would normally be hidden behind pillars or other structural elements. Architectural applications could transform how buildings interact with light. Windows that can become completely transparent or perfectly opaque on command could revolutionize energy efficiency and privacy control. Walls that can appear to vanish might create spaces that feel larger and more open than their actual dimensions. The consumer electronics industry shows growing interest in invisibility technologies for displays and user interfaces. Screens that appear and disappear on command could be integrated seamlessly into clothing, furniture, and architectural surfaces. Information could be displayed exactly where and when needed without cluttering physical spaces. Scientific instruments could benefit enormously from invisibility technologies. Telescope mirrors that cast no shadows could improve astronomical observations. Laboratory equipment that becomes invisible to certain wavelengths could reduce interference with sensitive measurements. Privacy applications represent another growing area of interest. Clothing or accessories that can selectively block certain types of surveillance while remaining transparent to human vision could protect personal privacy in an increasingly monitored world. Such technology could help restore balance between security needs and individual privacy rights. The timeline for practical invisibility remains uncertain. Some limited applications might become available within the next decade, while more general-purpose invisibility could require several more decades of development. The complexity of the challenge means that progress will likely come in gradual steps rather than sudden breakthroughs. International cooperation in invisibility research has accelerated progress by allowing scientists to share knowledge and resources. Researchers in different countries often focus on complementary aspects of the challenge, with advances in one laboratory inspiring new approaches in others. The intersection of invisibility research with other emerging technologies creates new possibilities. Artificial intelligence, could help control complex adaptive camouflage systems. Nanotechnology provides tools for building metamaterials with unprecedented precision. Quantum computing might enable the complex calculations needed for real-time invisibility optimization. Public perception of invisibility technology remains mixed, with excitement about beneficial applications balanced against concerns about potential misuse. Open discussion about the ethical implications of invisibility will be crucial as the technology continues to advance toward practical implementation. The dream of invisibility has inspired human imagination for millennia, appearing in myths, legends, and stories across every culture. Now, for the first time in history, that ancient dream is beginning to take physical form in the careful hands of scientists and engineers around the world. As current limitations are gradually overcome, invisibility technology will likely find applications that no one has yet imagined. The history of technology shows that breakthrough capabilities often enable uses that were never anticipated by their original developers. The young researchers currently working on invisibility problems will likely live to see their early prototypes evolve into technologies as transformative as the internet or mobile phones. They are laying the foundation for a world where the boundary between visible and invisible becomes a matter of choice rather than physical law. Future generations may look back on our current era as the time when humanity first learned to control visibility itself, to step in and out of the river of light at will, to become transparent ghosts or solid presences according to need and desire. As you settle into sleep tonight, let your mind wander through possibilities still undreamed. Imagine walking through tomorrow's world where invisibility technology has matured, where the dance between seen and unseen has become as natural as turning on a light. And in your dreams, perhaps you will glimpse a future where the invisible and the visible flow together like streams converging into a single river, carrying humanity toward wonders that await just beyond the horizon of what we can currently see.